Stuart and Tom, you guys have the floor then.
Hi, can you hear me okay?
Yeah, this is Lois.
Great. Okay, so we're going to be talking about our project for the STUOD hackathon, which took place in March online, and our project is on machine learning for El Nino prediction. So I'm Lois, and we have Tom and Stuart here as well, and we're PhD students with the Mathematics of Planet Earth CDT. So the hackathon, as I said, took place in March and was held online, of course. But we had more than 30 participants from across Europe. We had 12 teams, and then we had 7 facilitators and technical experts, and then a judging panel. So lots of people involved, and it was a really great event. So we had lots of kind of challenges that we could choose from these 3 kind of categories. We chose one from machine learning with weather and climate data. We were kind of given a lot of information and help at the beginning, and then we kind of set off to do the hackathon and approach these challenges. And then there was the technical experts available for guidance. So here are some of the comments that people gave after the event. There was some really great collaboration. There was lots of guidance, but nice open-ended tasks, and it was very well run and organized. So thanks a lot to the organizers. So our project was on El Nino prediction, and El Nino is characterized by when you have a warmer than average sea surface temperature in the equatorial Pacific, specifically this kind of yellow boxed region. That plot's showing sea surface temperature anomaly. And when you have that high sea surface temperature anomaly for more than 6 months, then that's classified as an El Nino event. And when it's colder, that's a La Nina event. So you can see this El Nino index on the right here. And that's showing the time series for about 70 years. And you can see that it kind of varies on timescales of like annual to decadal. And the red peaks are El Ninos and the blue troughs are La Nina events. And this seasonal oscillation has big impacts for global climate, and particularly for the west coast of the US. But one of the key features is that it's not very predictable. So our task was to try and predict the occurrence of an El Nino event in 6 months' time, given historical data. So our problem setup looks like this, where we had some data, some features. And for us, that was a representation of historical data at times less than t, for all available times t. And then the target we were trying to get to was this El Nino index, or alternatively, the occurrence, so a kind of discrete target, at the time t plus 6 months. And then the idea is you can find this model F that maps between the two. And there's 2 main problems here, which is how do you choose the best features to use? So if you just use every single piece of data available to you, your model will have way too many parameters and you'll end up overfitting. And then which model should you use? So use regression, logistic regression, linear regression, and Stuart's going to talk a bit about that later. So the data we were given spatiotemporal fields, so various things. We had sea surface temperature, sea surface salinity, precipitation, etc. And some of those are plotted here. But all of the data sets had kind of different lengths, which made it quite difficult because what you end up with is a lot of missing data, which makes finding that model quite difficult. And we also didn't have a huge amount of data points in time, so not too long a time series. So in the end, what we went for is just using sea surface temperature. I think it was the longest record, and obviously sea surface temperature is very relevant to the El Nino. But then how do you deal with the spatial data? Because you have all these grid points of data in latitude and longitude. And if you just plugged all of those into your model, you'd have an absolute ton of features and you'd end up overfitting the model, as I think Stuart will be talking about. So first, we wanted to reduce the spatial dimension of the data. And the way we did that was by decomposing the sea surface temperature data set using empirical orthogonal functions, or EOFs. And what you get when you do that is you get these modes of spatial variability, which are plotted in the top row. They're the EOFs. And then their amplitudes in time, which are the principal components, and they're plotted on the bottom. So what turned out really nicely was that the first EOF actually represents the El Nino oscillation really well. So if you plot that principal component against the El Nino index that I showed earlier, there's really good correlation. So the idea was we could then use the principal components rather than the spatial fields as features of the model. And another interesting thing that you can see here is in the mode 1, so the second EOF, and that is a kind of uniform warming. So that's presumably showing sea surface warming due to climate change. So those are our principal components. So that's how we worked out the features of the model. And then I'm going to pass you over to Stuart to talk about the model itself. Thanks.
Okay, so as Lois said, the idea was that we want to take this data and use some sort of machine learning technique to predict. So from the data at time t, we want to predict the El Nino index at time t plus 6 months, so 6 months in the future. And because the three of us at the beginning of this this challenge were fairly new to machine learning, we started off with well, the most basic machine learning technique, which would be like logistic regression. So the question we're trying to answer is, if we know the sea surface temperature field over the whole globe at time t, what will the El Nino, or will the El Nino index at time t plus 6 be greater than 0.4, which is the threshold to determine whether or not it's an El Nino year. So the data we have is 37 years of sea surface temperature saved every month, and we split this into 80% we use for training and then 20% for test data. So we can just simply apply the logistic regression and see what we get. So here I've plotted, so we have data starting from the mid-80s going up to 2020. And this black line shows the separation between the training data and the test data. So on the left, it's all training data, and we can see, as Lewis said, that it's overfitted quite a lot. But then if we look at the test data, it does seem to be doing reasonably well. So if you compute the accuracy, as in the fraction of the time when it predicts correctly, will the index be greater than the threshold, it gets it right about 83% of the time. And this seems pretty impressive, but if you take into account a model that just said it's always below the threshold, you would get about 74%. So put in that perspective, it's a slight improvement, but I think there's still more that can be done. So after logistic regression, the next logical thing to try is linear regression. So we have a similar problem set up, but now we take the field, the temperature field at time t, and we look at just computing the El Nino index at time t plus 6. So we have a continuous output for the linear regression. And then we can plot the results of this as well. And we see again on the training data, it's overfitting quite a lot. And then on the test data, it still does reasonably well, as we can see just visually from this plot. And the accuracy measure we used for linear regression was the R² score, which is a bit of a better measure than the accuracy we use for logistic regression, because this takes into account the fact that if you just predict a constant value, you'll get a 0 R² score. So this is giving 0.66, which is fairly decent. So 1 would be perfect, that predicts exactly right every time. So it's still doing okay, but again, we've got this overfitting. So we can, I'll talk in a bit about what we can do to address that. But first, just to compare the two methods. So this is just looking at the training data. And from the linear regression, we look at whether or not the index is above the threshold. And we return 1 if it's above, or 0 if it's not. So we can compare it with the logistic regression. We see they kind of produce similar results. And if we look at the accuracy, the linear regression is very slightly higher than the logistic. So now on to reducing the overfitting. So for that, we just focused on the linear regression because that one seems to be doing better. so far. So what we did is we used EOFs, as Lois said earlier. So what we do, we take our full time series of the SST data and use that to calculate the empirical orthogonal functions, which then decompose it into the components of the greatest variation. So we get them in order. So what we can do is truncate to the first n nodes to get the input data. So yeah, we split into a principal component, which is a time series, and an EOF, which is a spatial function. And we just choose the first n of these, depending on how much of the information we want to keep. And hopefully this should reduce the overfitting. But the question is then, how many can we choose? And fortunately, in this situation, because the data set is not really huge, we can just test out each value of n, just brute force approach, and plot the error, or the accuracy, sorry, for every possible truncation of the EOF series. And it turns out that if you choose a fairly low number of EOFs, you get a pretty good accuracy. There's a certain point where you choose, the more you choose, the worse you get. And then if you choose all of them, it sort of goes back up to good accuracy. So I'm not entirely sure of the reason for this dip, but from this plot we can see that the best choice is to choose 37 EOFs, which is compared to, say, I think we had about 450 in total. So that's a big decrease in the number of degrees of freedom, which also means that when we're doing the training, it will be much faster. So we just use this input data, and then we can do the linear regression again, as we did before. And we see that it does quite a good job of reducing the overfitting. So when we apply it to the test data, we see that it still follows the test data fairly accurately, but is not completely overfitted. And then we get also good accuracy on the, on the training data, it's not overfitted. And on the test data, it still does pretty well. If we look at the R² score with 37 EOFs, we get 0.6788, which is a slight improvement on the 0.6618, which you get from using all EOFs. So yeah, a bit of progress there. And now I'll hand over to Tom to talk about some other things we did.
Fantastic. So obviously this was our first kind of, or at least for me and a few of us, kind of our first time working with machine learning tools and real world data, for want of a better term. And so we tried a few of the other funky machine learning algorithms out there that you can find in your scikit-learn or your classic textbooks on this. And we tried them, and we tried using some other variables as well, but we found pretty quickly that this principal component analysis provided us the feature that was most useful. And so I think something we kind of, particularly tried a random forest say. I think there was some suggestion of trying out some neural nets, but really, I think we found over this project, and obviously it was time limited, that our time was best spent working on getting the right features and getting the right information out of the data, rather than trying to use an overcomplicated model or algorithm or anything like that. So we worked out pretty quickly it was best to focus our time and effort on working with these EOFs and trying to get them working well and seeing how best to use them in order to use the linear regression tools we had and get something out of that. But you could see using the random forests, we didn't get too far with that, but it was starting to pick up on some things. We'd need to obviously put a lot more into it to get anything out of that, but obviously it was a time limited project. So in terms of the conclusions, the EOFs were very useful in kind of collapsing this geospatial signal down into something that was much easier to work with, and so we could really reduce the number of features, which was really important. We ended up with those 37 principal components that Stuart mentioned, and these are much more easy to work with, while still retaining a lot of the important signal. We did manage to achieve some degree of accuracy using the regression based on these features. Obviously, we'd like to go further with that and see if we can work in some other features again. So this is still working all on sea surface temperature. We had a lot of other stuff in there that we could have used, maybe done principal component analysis on sea surface salinity or whatever as well. Or use of wind or tropical storms could be useful as well. And there are other indices for tracking El Nino. There are other things that might be useful within this that this could also be applied to. So lots of opportunities there for more things. And as this was kind of a 3-day hackathon project, I think it was useful for us to highlight what we had learned from the project. And the main thing we learned was that everyone involved in STUOD, both the people participating, organizing, the academics involved, everyone was really great. Everyone was friendly and supportive and organized a great event, as I'm sure you found this week as well. So that was probably the main thing we took away from it. Actually, it was just a great opportunity to, particularly in this last 18 months or so, talk to new people, talk about different things. And and for us, where, like I say, machine learning type tools, data science type tools are very new to us, managing data is hard. The data management's the hard part. It turned out, I don't think this was a huge surprise, but probably more of a surprise than we thought. Everyone likes to talk about their neural nets or their random forest or whatever. It was actually more important for us to get that clean data and interesting features rather than worry about model complexity. And then so like I say, choosing features as part of that is part of the problem. And we learned a lot about the relevant kind of Python modules, your X-array, scikit-learn, the bread and butter of how you actually go about doing this as well. But overall, we had a fun time. We learned a lot, both about the kind of specifics of this, but about how we'd go about solving problems like this in future. And it was really great to get a chance to work with Lewis and Stuart, and obviously everyone at STUOD. So thank you very much. And if you have any questions, now's probably the time.
Are there any questions for the hackathon champions, the returning champions? So I have a question. Did you think about comparing your predictions with these palm readers? These various indices, like something about some kind of shift in Indonesia that happens, and there are other correlations that are funny, like teleconnections around the world, in the Pacific, 2,000 miles away. There's some these things called indices. Did you know about those?
I certainly didn't. This was my first time looking at El Nino proper for this project, so I didn't. That sounds like a really interesting direction to look into. Lois and Stuart, did you have any thoughts on that?
No, I wasn't really aware of that. I mean, I suppose we're using global data, so I don't know. The hope is that it sort of takes into account everything, but I mean, so far I was just going from a sort of black box approach. So, but maybe it would be good to look into that in more detail.
Yes, having gone through the global data, then it turns out that there are, I forget what these indices are called, but all over the world there are these teleconnections that are called when something changes for example, when the other way around, when the El Nino happens, it changes the climate in Europe, it changes the droughts and and rainfall and so forth in California, thousands of miles away. That would be a really great project for machine learning, because the humans have sort of just understood that there exist these teleconnections, but there are there's no good explanation at all of these things. That's the word, teleconnection. You guys might think about that. Anybody else want to make a comment about the hackathon champions?
I have a question for you. You can just repeat it. That's probably easier.
Okay, all right.
So just, did you look into any of the statistical prediction systems? What you stumbled on is extremely close to what the state of the art statistical prediction systems do. They use a linear inverse model, very similar on EOF basis, with about 40 some modes. So it's extremely close to linear regression together with that. from with an all-time to all-time prediction. They get about 14 months of accurate prediction out of that system. So, but did you have any concept about how that was when you were starting out, or this was just take on this challenge that you didn't talk about any of the prediction systems that exist?
Yeah, no, I wasn't aware of that actually. I mean, we had sort of limited time, I guess, so we just sort of tried the things that seemed like the most straightforward to us. But
Oh yeah,
yeah, that's interesting to know.
one of the big advantages they have is that they don't just use sea surface temperature, they also have observations of the picnic line depth, and you can see the waves earlier looking in the picnic line depth and more clearly than looking at the surface, where storms and other things washes out the signal.
Yes.
Yeah.
So
Just for fun.
Baylor,
Okay.
what is picnic line? What is picnic line depth?
But they had this data in because we provide this data in the hackathon. But like they say, so picnic line is just the depth of ISO density, and
All of them, or only some of them?
we gave the climatology, the global climatology from the Argo that we could provide, and it's very smooth, but it's not too bad, and combined with altimetry and sea surface salinity, in fact, you can make a deal. But sincerely, I was personally very impressed by the capability of this young student to take to take this challenge in less than 2 days. So to be remembered, you did this in less than 2 days. So really remarkable effort. Thank you.
Thanks.
Yeah, congratulations. That's absolutely great. Yeah. So everyone remember these guys' names. They're going to be on the market in a year or two. Okay. So thank you very much. I guess let's take a couple of minutes break and 2 minutes until 11:25. Okay, and we'll start up again.
This one's still on.
So Dan, and Etienne and Chap, it's our turn to make some sort of comments about forward thinking, I understand.
We
So could you lead it off, Dan?
we had this beautiful.
Can you hear me?
Yes, now, yes.
Okay. Okay, so before we start, Daryl, I want to make the announcements regarding the proceedings and the white paper. Is that okay?
Yes, please.
Okay. Shall I start?
Yes.
Okay. So before we go into looking into what is next for us as a group, as a project, I have a couple of announcements. The first one is that we have signed a contract with Springer to produce a series of proceedings following each of the annual workshops. And we will start with the one that is just finishing now. And Springer has kindly produced a flyer for this series of proceedings. They will appear within the series of Mathematics of Planet Earth. And, this kind of things, I'm sure are probably well known by now. They sort of match, the statements here match exactly what we have, on our agenda for the project. There will be open access. So I'm sure, it's sort of, what this means, everybody will be able to download them. And so this will ensure they will have an immediate impact on research. The plan for these proceedings is that we ask all the participants in the annual workshop to submit a short paper, somewhere around 10 pages is the plan, and we will invite not just the speaker, but all members of the advisory board to submit a 10 pages paper if they want, if they wish to do so. We encourage everybody to do that. We hope that these proceedings will have a high impact on the literature because they will sort of bring together a lot of expertise from all different area, and there will be a lot of interdisciplinarity in these proceedings. Yeah, that's all I wanted to say on this. Is there anything else related to the proceedings that I should add, Daryl, Etienne, and Bertrand?
No, that's perfect. I think you said everything.
Okay.
We have really very high hopes for this series. There's going to be 6 of these volumes, and so it's going to track the project's history, but also it's going to be tracking the developments in this field, for a significant amount of time. And once we start laying down these results, it'll be a story about how this thrust in research and mathematics of planet Earth has evolved. So I think it's very important for everyone in our advisory board to make clear what directions are available and what the basis of the project is from their viewpoint. And as time goes on, things will weave together. They think of it as an opportunity to make a continuing story.
Right. So there will be Anna is going to send a formal invitation to contribute to the proceedings, and you know, at the moment the plan is that we will ask for submissions to arrive by January, and Springer has promised that we will have a very fast turnaround, so that, you know, within 6 months of the submission, we will get the volume published, at least online. They will be refereed.
Yeah.
And you know, there's going to be another deadline for getting the reviews and so on. But we will put all these details in the letter of invitation. Okay, so that was one thing, and another thing which I want to mention is that we run these monthly Sandbox meetings, and I thought I will put up, you know, one of them. So this one is Sandbox number 6. Let me try and find out. Oh, it took place in February. So we go to Sandbox number 10. So the standard setup for the sandboxes is that, you know, we have 2 sessions. In the first sessions, we get talks by members of the project. So, you know, in here you can see that Etienne gave a talk, Juana gave a talk, Longlead gave a talk, Giles Tissot gave a talk, and then Camilla, and then we have a break, and then we invite a member of the advisory board to give a talk, and then we discuss the white paper provided in advance by them, and sort of, it's a nice discussion, and that's our way to involve the advisory board on a continuous basis. So, you know, this comes, so, you know, the members of the advisory board will receive an invite to submit a white paper at a time of their choosing. The earlier the better, and then we will schedule an invitation for them in the in one of the months for one of the monthly sandbox meeting. So, you know, it's really a warm invitation for the members of the advisory board to submit the white paper. We take these things very seriously, and, you know, have great discussions, and you know, we look forward to have the members of the advisory board coming to our sandboxes, not just the one that, you know, for which they are sort of the invited speakers, but to all of them.
Yeah, well, so what we're really hoping for is that, you know, everybody will be engaged. All of the advisory board will be engaged in the sandboxes, and they will start having joint papers together with you guys.
Okay. Yeah, I guess these are the 2 announcements that I wanted to make. What I want to do now is just put up this page, which is essentially taken from our project, and, you know, on the left hand side, you have this series of objectives where, you know, we start from the bottom and going up, and then you will be able to identify and see that, you know, there is work done at least in the first 2 objectives. In other words, data analysis techniques relying on stochastic transport and stochastic model describing the dynamic of the upper oceanic surface. And the plan is that, you know, for the remaining 5 years, 4.5 years, we're just going to go up in achieving all of these objectives. And the other thing that I would mention is, this is something which I mentioned on Monday, that this is, our research is not a linear one, but is a cyclic one, where, you know, sort of go go through models and combine them with data and see how good they are, and then we're going to improve them again and going through the cycle repeatedly. So that's what I want to put. This is kind of like the basis of the discussion. So I'm going to let Dari lead the discussion. Dari can take it away.
Okay. So you see where on the special already during this meeting, we've seen some beginnings of large-scale computations. And so that this, and we also have finished calibrating some of the models, the models that in the 2D models. So what I'd like to do is call on people to among the PIs and among the postdocs to talk about their the present situation and how we're moving on to the next level. You heard from Stuart and I forgot who spoke about Nemo. Stuart spoke about this idea of making the transition into stochastic modeling in the community codes is a serious idea. It's going to be a big undertaking, which will be a theme. And it's going to and what we found out with the lower dimensional models is that the lower dimensional models have to be modified and changed, understood from more than one direction in order to just get to the point of preparing the EOFs and preparing these kernels for understanding the modes of the core skills that are describing the effects of the fine scales. So his way here, in a way, maybe could you make just a few remarks about about the calibration for TQG and what's next with TQG?
Yeah. So I use the string function to do the calibration. So that was on my slide. I'm sorry, I'll close my door first. It's a bit noisy. Sorry, give me 1 sec. So to do the calibration, we need to extract basically the large features. And then from that, we can then compute the fluctuations. We are in the process of discussing how best to do this. But at the moment, we are sort of using the PDE operator to do. But also, like what's being discussed is using something like the Gaussian kernel, for example, as a convolution to do the smoothing. And the benefits or pros and cons of the different approaches, this is up to discussion. And also, I think yesterday during our networking session, Bertrand touched upon the fact that the sort of the memory within the different scales. This is also something quite important and affects, for example, the representation errors that Dan and Sebastian were talking about. So it's not a simple issue, and these things have to be really treated very, very carefully. Yeah, so but for the moment, for the TQG model, I'm using the Helmholtz operator, tuning basically the regularization constant to match the resolution of the grid. And then that sort of filters away the higher frequency unresolvable scales. And then from that, we can take the difference between the coarse grain version and the fine resolution one to get the fluctuations. And then for now, we're using EOF analysis. But we'd like to sort of explore some of the rough path ideas as well. So yeah.
Yeah, so we can see, from what Wei said, you can see that already at, in the 2D level, we can see so many other open paths for research. However, we know that we have to deal with satellite data at some stage, and already at the 2D level, asking how do you do data analysis and then move on to data assimilation when the data is laid out on tracks, and the tracks, and the data on the tracks have correlations in space and time. Okay, so that's one of the features, I guess it's common to all research, that things are, more things than you expected are happening, even when you expected more things to happen. So anyway, we're at that threshold for moving to 3 dimensions, and we're also passing to the situation now where we start talking about what is the data structure for real data. So maybe Bertrand, will you say something about what you expect to be able to bring in for this to help us with this real data, and what do you see as and I know we heard from several people at IFREMER about the machine learning approaches to data management. But can you say what are the next things which are on your threshold?
So many things to do. Indeed. Okay, so different aspects are running in parallel. Besides okay, for assimilation purpose, where we are trying to make progress is really to develop. And this was not shown over the last 2 meetings, and I hope will come in the last 3rd meetings. Is this effort to take fully into account the observation, or the model for the observation. So meaning that building this so-called OSSEs, where you try to evaluate the impact of the next generation or the actual generation of observation, but into a model, we need to have a forward model of very high quality of what the instrument is really bringing, and then from this, improving a lot the way the data will be handled in the assimilation. So far with Dan or with Ronan, so Dan from a theoretical aspect, and with Etienne and Ronan from a more technological aspect with machine learning, they deal already with a product. That means that sea surface height, sea surface temperature. So okay, but before this, and this is where we will learn a lot. In fact, most of the measurements are very indirect. So you don't measure easily sea surface height, sea surface temperature, salinity, surface waves, internal waves, and so on. So you go through a model for this observation, and this is what we can bring, and this will be really relevant to the effort that is currently done by Wei to stipulate the error of both the inherent to the instrument and the observation, and the way the observation is indeed captured by the instrument within the model. So like you say, the time-space sampling is introducing some errors. And okay, so this is one step that I think will be very, very important for assimilation purpose in the next 10 years or even more. and it will be a part of the effort of STUOD to make it clear. And okay, so this is where we will have most of the effort next year. So that's on my side, at least, to bring a better knowledge of the instrument capabilities inside the assimilation project. So that's one side. And you, Etienne, will you support my criticism of any of this model you developed?
I don't know. No, well, not okay. So as for me, for the next year, I think we will have to develop maybe techniques that would allows us to, for example, to specify a dynamics for the noise. We have learned so far that when you use stationary assumption for the noise, even if you calibrate finely the noise from high resolution data, okay, it improves. But what is missing is often some kind of dynamics for instance, for the variance of the noise or for other characteristics of the noise. So, of course, we have used, for instance, well-thought projections sometimes, and these kind of projections they have enabled us to bring some dynamics within the fluctuations, but I think it's not sufficient. We need to have some proper dynamics for the noise. So the idea would be to go in one hand toward machine learning for specifying this dynamics noise model. Other tracks that could be followed is also to build noise, and that's what we have started with Dan, to build noise that would be useful for data assimilation, meaning that they will allow us to go toward the next observation. So that's data-driven specification of the noise in order that the data assimilation is simplified. We have seen that maybe what is missing is also some kind of waves components in the noise. So we would like to add in our model such kind of component in the noise. Another idea would be also to add noise that allows us to regularize the dynamics we have underneath. So, for instance, add noise in such a way it in some way allows us to implement a Luray regularization. And I think this can be done through this modified advection. So specifying a noise in order that you have some kind of smoothing of this nonlinear advection that is performed. So that's another idea. Okay, so yeah, I think I.
So what about simulation?
Yeah, of course, it's another objective. So I talk only about the noise specification. Yes, of course. All this is in the same time with the objective of data assimilation and the use of real data and realistic model. So
I mean numerical simulation.
Yes, and we have the objective also to go toward improved simulation with stochasticity, I hope. So yes. Was
I
it
think
was it
beginning with Nemo? This beginning with Nemo is a tremendous.
Yes, of course, and we hope to go forward this year in a significant way, we hope, to have that kind of simulation ready. Yes.
Yeah. I think that
but
real
clearly between us, clearly we need to address theoretically the fact that the so-called noise is in fact the key evolution since the work of Etienne and Daryl put this very well for introducing the noise. We know, in fact, that in order to check for the consequence of this noise onto the resolved scale dynamics, it means that, in fact, we have to deal with the evolution, the space-time evolution of this noise, and this has to be. This will be indeed a key to better understand the real observation. The model is a model, okay? You will put in a model what you put in at the first, but in the observation, you will have to deal with this uncertainty around the noise. So model is fine. This is too open for the community, but there will be no other things that what you introduce it. And so this, you will not learn anything from the model. It's just a bridge with the community. So, but to deal with the real data, we have to make progress into the theory.
So Dan, maybe you would like to chip in.
Well, okay. So we have to understand this. We're talking on one. So the noise. I think the noise that Etienne was mentioning is the stochasticity in the model, and yeah. I think Bertrand refers to the measurement noise. So the stochasticity in the data, the random perturbation, and try to understand the randomness in the data. So these are both very, very important, and there's some linkage, but there's understanding both of these is something which is crucial to the success of the projects. And the more I learn about these things, the more it seems to me that somehow the community, we're saying we do data simulation. We're saying we do nonlinear filtering where we just sort of concentrate on the signal. We just concentrate on the actual truth, but it's more and more apparent to me that we should concentrate on the noise, because once you understand the noise, then you know what the truth is. So I think in some sense the community as a whole should be looking at understanding the measurement noise, and as an outcome of that will be also that we will have a better way to estimate the model. So the noise it is really crucial, and I think we as the project we have to allocate resources to understand both the noise in the model, in other words, the stochasticity in the model, and the measurement noise, in other words, the noise in the data. So, and we can't do anything. If you talk about data simulation, particle filters, if we don't understand this, then if these are not properly calibrated, then there's no way we can get something which is meaningful. So
Dan, what you just said, so are you planning to use data simulation in this context also to actually learn the stochasticity of your models?
I think we're already doing that. I think Etienne is already doing this.
Well, in simplified model, but yes.
So the
Because
point is
this
we have
seems
to
to-
model not just the signal, but also model the noise.
And the stochasticity of the model induce something on the space-time sampling of the data. So the data, so that's what you call noise is not necessarily the fact that the instrument is bad. It's just like the way you sample your stochastic model is introduced an aliasing or whatever you call it. And this is really what we have to deal with and to understand theoretically first.
Yeah,
And
so that gets maybe back to what I just said. I mean, when you want to match your model, I mean, it's also in the end it's a numerical model, right? So it has all these sampling issues, etc. And then you want to learn the stochasticity in your model from the data you have. And then it's the question: do you have to filter, for example, the data before you use it, or use the data as it is, etc.? I mean, there's tons of interesting questions there. But it's I think to your project, it's much more fundamental than saying sort of the classical data assimilation perspective, where you say, "Oh, I have a model, and now I infer the states of the model."
Yeah, I couldn't agree with you more. I mean, you know, it's really, I mean, you can't do the data assimilation unless you get the model right.
Well, I think it is already data assimilation, right? I mean,
well, okay. I mean, it depends
whatever.
what you mean. Yeah, I agree. I mean, you know, it depends what you mean by that. You know, sort of, if it's just a matter of sort of data assimilation means understanding the model, then you are actually doing already data assimilation. But you know, the kind of thing that, you know, ATN students, Benjamin they're involved now. That's what they're trying to do. So try to understand the noise, the stochasticity through data.
Or learn, right? Understand, learn, yes. Yeah, but there's also a question, I mean, do you want to, I mean, you should use some summary statistics to fit the model. What kind of metric you're going to use, right? I mean, how do you decide, you know, how well a model fits? I mean, likelihood is probably, I mean, it seems like that's the most natural one, but I'm not sure if it's actually doable. I mean, if you have a meaningful likelihood for the reasons that Bertrand mentioned, right? I mean, all these fuzzy things involved that you think you have a likelihood, but the forward model is not known really, and lots of stuff. So,
well, Etienne, do you want to comment on what you're doing with Benjamin?
Yeah, the idea is okay. The idea is to specify the noise in such a way that your nest of particles or ensemble members go toward the next observation, and so it's like nudging, but instead of adding an external component in which you enforce this guiding when you do nudging, then here you only specify the noise in such a way you guide your particle, and you make sure that the spread is sufficient, for instance, to incorporate the new measurements that you will have.
yeah, but that's different from what I had in mind, right? I mean, because I was thinking of something more generic. I mean, you're not using a particular sort of, you're not trying to hit a particular observation or something. And
no. No, what we're doing is okay. We try to see how well the current observation at time t is well, and the current solution that you have, so with the noise, is able to explain the next observation. So as there is a discrepancy between the transported current observation and the next observation is small. So that's the idea, and to do and the unknown of this, well, of course, it constitutes some kind of cost function, and you minimize this cost function in terms of the noise parameter. So that's only the noise that you specify in this way.
But you do this over many observations, so you try to find a generic expression for this, or is it really stepwise as in particle filtering, like optimal proposals or something, where you sort of
it looks like optimal proposal. I agree. It's the same. It's exactly the same idea, and we use all the observation available, meaning that if you have gridded observations, for example, it's not only punctual. You use the whole set of observations.
Sure. Right.
Yeah. It's more easier indeed to use this, the whole all the observations on the grid. It's much more easier to define robustly some coefficient for the noise, such as all the observations are well represented by for example, the spread of your ensemble.
Mm. Well, it's sort of, practitioners try to do this by these variance inflation techniques, and I think that's
exactly. Yeah, exactly. It's
actually, I think multiplicative inflation you can write down, I believe, as a multiplicative stochastic driving term, defined by your ensemble, actually. Maybe that's actually something we can explore at some point, because I think there is some deep. I mean, well, not so deep maybe, but I think there is a connection. Of course, they do it very ad hoc, right? So it doesn't have these conservation properties that you build into it, but the intuition is about sort of right? So you have a multiplicative noise. You need definitely multiplicative noise there.
Yes.
And the only meaningful quotation mark you have, information you have is in your ensemble, and you then tune it so that it's well aligned with the uncertainty in your data. So you match the noise in your ensemble or model-driven noise with the data noise, and they tune it. They fine-tune it. I mean, they really tune this to the end so that both fluctuations agree with it. I mean, you know all this, right? So that's exactly what practitioners do in the end, right?
Yeah, exactly.
And it's calibrated. They call it calibrated, and they're happy, right?
Yeah.
Okay.
There's another feature, Sebastian, about this noise. This is not just multiplicative noise. This multiplicative noise multiplies more than just the solution. It multiplies the gradient of the solution. So these methods you're talking about will have to be extended to the multiplication of the gradient, because that's the transport.
Yeah, no, I'm not saying that but I think that's an interesting perspective, because I mean, also, if you want to talk to the practitioners, I mean, it's good to connect to the method they're using and to say, what is the difference? What is different? Why is it that your methods have, an advantage? And maybe you can even say, oh, I mean, it's not so different from what you're doing, right? And they're much more open to what you're suggesting, maybe. Because, oh yeah, I mean, we're doing something similar, but this is a much more clever way to implement it. So I think that was also Alberto pointed it out yesterday, or in his remarks. He wasn't there yesterday. He said that try to connect more strongly to the methods people use and try to put them into your framework, or at least put them into perspective, and then maybe there's a lot of synergy to be gained from making these connections.
Yeah, that's what we have tried to do with Benjamin, for instance, and Dan, to show that stochasticity may improve the classical ENKF setting, because you're in a way you are dealing within the dynamics to this kind of inflation problems you have when you have to augment artificially the spread of your ensemble. Otherwise, it breaks down. So this is included in a way in our dynamics. We have less problem to fix the magnitude of it. So it's a bit more robust and leads to better results. And it's not, I mean, it's a bit more complicated because you have to encode inside the dynamic this noise inside the code. but yeah, okay. So
yeah, no, but I always preferred this anyway. I mean, I always found it strange that just before you do the data assimilation, you suddenly bang, you sort of inflate and
yeah, and what I would say is, I mean, you don't know really what you are doing when you add some additive noise. You don't know really what you're doing to the dynamics. You don't know how much you are going far away from the classical attractor, for example. You don't know if you respect the deterministic dynamics you want to emulate behind this. It may change a lot. So yeah, that's what we have shown, for example, even for a simple Lorentz 63 model. If you add, I don't know, multiplicative noise on the temperature and the velocity component, then you get at the end PDF of the solution that are completely different from the deterministic system, even for very low noise. And if you do at the opposite, you add let's say physically consistent noise, then you stay on the attractor, and it's much more reasonable, because you for small noise you stay very close to the deterministic attractor, so you have this guarantee. I think.
Yeah. Anyway, I guess it's a nice discussion to follow up on another occasion, maybe, because I think there is actually this I mean, if you take, for example, you can look at the time continuous limit of this multiplicative inflation that meteorologists use, and you can actually write down an SDE formulation for it. I think that's, I mean, the Fokker-Planck at the weak perspective, it's actually can be reinterpreted. And I still believe it's a pretty clever way of actually, in particular, exactly to what you said, with staying on the attractor, because if all the ensemble members are on the attractor, yeah, I mean, you can push yourself out, but it's still a reasonable direction to go. But yeah, anyway, there are lots of interesting stuff there.
So does anybody else on the advisory board want to make some comments? Speak now. No? Okay, then I guess we should close the session then. And thank the organizers for, you know, really the person who is most responsible for all the success of this workshop is Anna Radowska. I don't know if she's here, but we all know that she's the driving force for our project. Any other final remarks at the end?
No, I want to thank everybody. It was a very nice week, I think. There were great discussions. So now we have to chew all this, but yeah, that's.
So we look forward to your white papers. And, you know, I'm looking forward to seeing you during the year. So, yeah, Bertrand, did you want to make any final remarks?
No. I concur with all your view, and I thank again the effort from the organizing committee and Anna and all the people helping her to put this together, as well as the external board, obviously, and looking forward their question and remarks. And also keep in mind, Sebastian and all, that we are really listening to your advice and willing to indeed progress with you. So thank you again, and thanks also to the young scientists that they gave excellent talk, and it was not so easy on a limited time. So okay, thank you again.
That's great. Okay. Dan?
Yeah, I mean, same as with you and Etienne and Bertrand. First of all, our thanks to Sebastian and the entire external advisory board. And it's not easy to go through 50 pages of a report in a short time. And I hope they sort of took some enjoyment in seeing our progress to date. We're still at the beginning. We're still the new kids on the block, and we find the sense that there's no legacy. We don't have to obey by any rules, and I think this is the ideal mind frame to come up with revolutionary and not evolutionary ideas. We should thank everybody, all the speakers, not just the speakers from the project, but also the members of the advisory board that gave talk, and in particular Sebastian and Franco and Onico and Alberto and all the other members that they gave the talks. And we had some very interesting discussions that will be followed up in the forthcoming Sandbox meetings. And also don't forget about the hackathon. People, we're going to organize the hackathon coming up this coming March. We'll send the call around, and if we're going to invite students from all over the world. This is not just an activity where the CDT students, the MPhD students are participating. This is an activity for students all around the world, and we found that we had people from many other countries, and we plan to continue. This is an example of good practice. I'd like to thank personally Anna and Wana. Both of them really worked very hard. And we had last week, there was, I think, almost every day trying to check and sort out the system. It's the first time when we did a mixed mode presentation, and that's not an easy feat. But we made it work in the end. Also yesterday we managed to sort out things. Rosemary, it turned out that Rosemary actually was not getting any of the emails, so that was the problem. But Bertrand convinced Ronan to take over, and it worked out well in the end. But it wasn't an easy day yesterday. Baylor is gone, but it was great to have Baylor. I mean, honestly, Baylor, thanks a lot for being there with us. We had lots of discussions, and we had some nice dinner, and hopefully next year we're going to have more members of the external advisory boards and other participants that will be in person there, and we will be able to sample that 2006 Rioja that Daryl is threatening us every time we meet. So I'll stop here, and thank you very much, and see you next year.
Okay, see you next year. Thank you very much.
Bye.
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 Bye-bye.
Bye.
Bye-bye.
Bye-bye, Anna. Bye-bye, Wana. Very good job.